Okay, yeah, test Wednesday. Woo!
You mean this Wednesday?
Yeah. Yeah, this Wednesday. Sorry, guys. This is what we're going to review today. And last time I gave out a Chapter 13 quiz, and I didn't this time. So what I will do is I will give out a Chapter 13 quiz, and I'll post solutions, and you can do it just to see what kind of questions I would ask, because there's no 13 review on here either. And we don't want what happened with Chapter 9 on the last test to happen with Chapter 13 on this test, right?
Here we go.
Okay, and I think, actually, just because it's the end of the semester and I feel nice, I'll put out that quiz and I'll make it extra credit. Okay? Like, I might not, I haven't decided how much, but I'll make it a little bit extra credit. And I recorded myself saying that, so now I have to do it.
Just
So,
stop recording, rewind.
I'm not going to go back on what I said. I'll make it like a little bit of extra credit. So for each of the following research questions, would it make more sense to collect paired data or independent samples? So women give their actual and desired weights. An estimate of the mean difference is desired. That's definitely paired. All right, 2 treatments for reducing cholesterol are compared. 40 people with high cholesterol use the first treatment, and 40 people with high cholesterol use the second treatment. An estimate of the difference between the mean decrease in cholesterol for treatment 1 and the mean decrease for treatment 2 is desired. This is 2 different independent samples, yep. Well, it is given in the directions. I'm sorry, that was a little bit sassy.
Perfect.
Yes.
Okay, when's the exercise?
Can I write an announcement in Blackboard and make decision about that then?
Oh, okay.
I mean, I haven't even posted it, but it will be due before your test.
Okay.
So Wednesday. Okay. So do you guys have your T-star tables? Maybe? Oh, I know, so hard. Okay, so if we're finding, so section 11, chapter 11 is finding confidence intervals. So if we're finding confidence intervals, we need multipliers. So if we have degrees of freedom of 100 and 95% confidence level, just tell me what the T-star is going to be. I got 1.98. Y'all see that? Yes, no, maybe? Yes, okay, I got 1 thumbs up at least. So on your, you look at, I don't know what this one's called, but it's not table 8.3, it's the other one, right? So you go to the 95% confidence level and down to degrees of freedom equals 100 and 1.98. How about for n equals 41, 90% confidence level? So what's your degrees of freedom? 40, okay. Let's see, so over 40, I got 1.68. And this T-star, this is your multiplier when constructing your confidence interval for means, right? Yes? Okay. Each man in a random sample of 9 men between 30 and 39 is asked to do as many sit-ups as they can in 1 minute. The mean number of sit-ups was 35, and the standard deviation of the number of sit-ups was 7. So find the standard error of the sample mean. What's the formula for standard error of x bar?
Standard deviation divided by the root number.
Yep, root sample size, exactly. So what goes in for your sample standard deviation?
7.
And how about your sample size? So that's 7/3, or I got 2.33. Is that part okay? All right. Part B says to find the confidence interval of population mean. So this will be x bar plus or minus your multiplier, which is T star, times standard error of x bar. So you know what x bar is, right? You know what standard error of x bar is, right? What do you need to find still? T star. So how many degrees of freedom will you have in this case? 8. Great. So degrees of freedom is 8. 95% confidence, what do you see T star is? 2.31. I agree. Do you guys agree? Okay. So we have 35 plus or minus 2.31 times 2.33. It's approximately 35 plus or minus 5.38 or 29.62 to 40.38. I think I copied your test and didn't specify how you should round, so I'll have to make a decision on that day, but I'll look through the data first. So if I don't specify, I won't be very picky about it either, though. Does that make sense, though? Does that seem like a reasonable guess? Okay. So write a sentence that interprets the confidence interval in the context of the situation. So we'll say with 95% confidence, the average number of sit-ups men aged 30 to 39 can do in 1 minute is between what and what? 29.62 and 40.38. It's reasonably wide range. How could you make your range around your average narrower?
Larger sample size.
Larger sample size. I mean, 9 was pretty crappy, right? Yes. Okay. Ready for the next one? Yes? Okay. For a sample of 20 women aged 19 to 29, responses to the question, how tall would you like to be, are recorded along with their actual heights. I think it isn't a huge surprise that most people want to be taller, unless you're already 6 feet tall, in which case it would be shorter. So the mean desired height was 66.7 inches, and the mean actual height was 64.9. So the mean difference D bar is 1.8 inches, and the standard deviation of difference is 2.1. Is it clear this was paired data? Okay. Find an approximate 95% confidence interval for the mean difference between desired and actual height, and write a sentence that interprets this. Okay, so we have our D bar plus or minus T star times the standard error of D bar. We have to find all those pieces. It's just D bar instead of X bar. Just explain it, just because we have differences. So what do you want to start with? Standard error? Sure. Well, and D bar we're given is 1.8, right? Okay, how would you find the standard error of D bar? Pretty much the same as the other way. Is this just S sub D over root N? So what goes in for S sub D? And then for N goes 20. So I got this to be about 0.47. Okay. And what's the last thing we have to find? T star. How many degrees of freedom do you have? 19. I think that's actually probably even on your table, isn't it? So what's your multiplier? Great, 2.09. Awesome. Okay, so we have 1.8 plus or minus 2.09 times 0.47. Oops. 1.8 plus or minus 0.98. And I'm afraid to need your help because I made a boo-boo on my notes here. What's 1.8 minus 0.98? I think it's 0.82.
2.7.
Yes, 2.78. Okay, and a quick sentence to interpret that. So state your confidence level with 95% confidence. Women want to be taller or shorter than they are. Be between 0.82 and 2.78 inches taller than their actual heights on average. It doesn't mean every single person wants to be taller. It just means, generally speaking, most people want to be taller. Okay. Explain why the following statement is not correct. On the basis of the confidence interval computed in Part A, we can conclude that all women would like to be taller. Which part of that is wrong? All. Because this is really a statement about the average among all women. Does that make sense? So how you would change it, or what we can conclude women want to be taller on average, not necessarily all. So we've had a confidence interval for one mean, a mean of paired differences, and now we're going to have a difference of means, so to kind of get all the bases for means. So for a sample of 36 men, the mean head circumference is 57.5 centimeters, with a standard deviation of 2.4. And for a sample of 36 women, the mean head circumference was 55.3, with a standard deviation of 1.8. So find the value of the difference between the sample means for men and women. Here's men minus women. Okay, so is it first of all clear that these are two different populations?
Yeah.
Okay, so the difference, x1 bar minus x2 bar, so men's head circumference on average was
57.7.
Minus women's, which is 2.2. I mean, maybe you're a hat designer, you want to figure out like how much bigger should you make those men's hats? Is that a reasonable question? Maybe? Okay. So find the standard error of the difference between the sample means in this context. So I didn't say to use the pooled standard error, so you don't have to. Do you remember what the standard error for x1 bar minus x2 bar was?
The first standard over n1 plus the second standard deviation over n2.
Only difference is they're squared, because they're inside the square root, not outside of them. Does that ring a bell? Okay. So what goes in for S1?
2.4.
So you got 2.4 squared over
36.
Plus
1.8.
over
36.
36. And I got 0.5. Someone should check that, but it just worked out so perfectly, it seems like not a coincidence. Yeah, okay. Awesome. So now because we didn't pool these things together, when you talk about your degrees of freedom for the next one, what are you going to have to use?
Smaller one minus one.
The smaller of the 2 minus 1. In this case, both samples were 36, so your degrees of freedom will be how much?
35.
35. Okay, so our confidence interval here is x1 bar minus x2 bar plus or minus your multiplier times the standard error of x1 bar minus x2 bar. Is 35 on your table? No, it's not. So let's just go between 30 and 40 and then average. So for 30, I have 2.04 for a multiplier, and for 40, I have 2.02. Let's just use t star equals 2.03. Okay. What goes in for x1 bar minus x2 bar? 2.2, okay. Plus or minus times 0.5. That's 2.2 plus or minus 1.015. If I was going to round that to 2 decimal places, what would I round it to? 1.02. It's okay. It's hot in here and we just had too much turkey. 1.02. So I have 1.18 to 3.22. So do men have bigger heads than women on average?
Yes.
Yes. Does that mean all men have bigger heads than women? No. Okay, just sometimes. Okay. Not so bad, right? Okay. All right, find SP and then find the pooled standard error. So this SP is just a formula one probably should write down. I don't have it memorized either. But you use this when your standard deviations are approximately equal. So, I mean, in this case, these numbers don't appear to be super close together, at least not. But let's just do this and see how different the interval is. So this is n1 minus 1, s1 squared, n2 minus 1, s2 squared, over n1 plus n2 minus 2. I think you had to use this on a homework problem, didn't you? Meanie.
I just realized I did it wrong and now I'm all mad at myself.
I'm sorry. All right, what goes in for n1? Okay, so that's going to be 35 once I subtract, right? And then s1 is plus 35 times all over 36 plus 36 minus 2. So after much calculator punching and putting parentheses here around the numerator, I got 2.12. You must get that? Someone said, I think. Maybe no one's. That was a phone? Oh, okay. Someone's phone went off. And the funny thing about, that's not funny, but this, the thing is you do all this work to get this SP, and then you have to go back and find the standard error of x1 bar minus x2 bar, which is an easy thing to forget. And the difference now is you use SP squared over n1 plus SP squared over n2. And they're so close together, it's kind of crazy. I just chose to not round to show you how close they are. 0.4997. Okay. I think it's really, really easy to. It's so much work to find SP, you kind of forget about the step. Does that make sense? That's my experience. That's what happened to me when I did my homework. Forgot that step, and then I looked at my answer key and I'm like, oh crap, it's wrong. Okay, and then once you have that, is the confidence interval very different? No, not really, except the one thing that does change are the degrees of freedom. Remember that it's now n1 plus n2 minus 2. So I think that's what 36 plus 36 minus 2 is. So your multiplier is now different. 1.99, yep. So you got 2.2 plus or minus 1.99 times 0.4997 is 2.2 plus or minus 0.99, or 1.21 to 3.19. Was that very different? No, it wasn't. Okay. I think this would make a much bigger difference if your sample sizes were really small, like say like 10 and 10. It will really decrease your multiplier to pool them together in that case. Okay. So in a nutshell, that's chapter 11. So can you find confidence intervals for means? Yes? Okay, I forgot about proportions from last time. Now let's do some hypothesis tests with proportions. Okay. So suppose that the present success rate in the treatment of a particular psychiatric disorder is known to be 65%. A new research group hopes to demonstrate that the success rate of a new treatment is going to be better than the standard. Use the letter P to represent the success rate of the new treatment. Write the null and alternative hypotheses. So the kicker is in this question, a lot of you got this wrong on your quiz, they gave you a null value. They told you what the baseline get better rate is. So H naught is nothing going on, your treatment not better than the new treatment, which means your proportion of success is equal to what? 0.65. Or proportion of success on new treatment is the same as on old treatment.
So is it wrong to say less than or equal to?
Less than or equal to is also fine, as long as you get the or equal to with this one. HA would be the proportion that experienced success on your drug is greater than 0.65. Proportion of success on new treatment is better than the old. Okay. So consider testing the null hypothesis that there is no relationship between smoking and getting a certain disease versus that there is a relationship, that smokers are more likely than non-smokers to get this disease. So what would you conclude if the p-value was 0.35? Could you reject H naught, or would you not reject H naught in that case? Fail to reject H naught. So we cannot conclude smokers are more likely than non-smokers to get this disease. Is the only reason the p-value was that big that smokers just don't get the disease more often than non-smokers? Or could there be another reason that p-value is big and really the smokers could be getting the disease more often? If you have a small sample, you might get a big p-value even though there is relationship. And, okay, if the p-value is 0.04 and the level of significance is 0.05, then what can you conclude? In this case, you can reject H naught, accept HA, and you conclude that smokers are more likely the disease and non-smokers. Okay. All right, for each of the following, find the Z statistic. So we have a sample size of 30, a sample proportion of p hat 0.7, and H we're testing H naught as P is equal to 0.5 and HAP is not equal to 0.5. So let me just write out what the Z statistic is. The Z statistic in this case is p hat minus p naught over the standard error of p naught. Now, how is that different than a T statistic? Because we're not going to have to review this other than now. For T's, we're talking about means, right? So that's X bar, right? Minus whatever your null value for your mean is, right? That could be 0, could not be 0. And what goes in the bottom there? Standard error of
X bar.
And notice how one thing that's a little bit different is that you actually know what the null value is in this case, this P naught, so you can find the standard error of P naught. To find the standard error of mu, you'd have to know sigma, and you don't know what sigma is. Just see what I'm saying there? So that's why, like, which thing you get the standard error of is different in those two cases. But they have the same basic structure, right? Okay, so we'll keep this in mind. That's what our Z statistic is. And we're told some stuff, like what's p hat? 0.7. What's your null value? 0.5. And then how do you find the standard error of that null value?
That would be the p hat times 1 minus p hat divided by
It's p naught, 1 minus p naught. That's the one difference over n. Because you say, if my p naught is this, how strange is that p hat? So in for p naught goes 0.5. 1 minus 0.5 is 0.5 over n, which is 30. This comes out to be 0.0913. So then your Z statistic is 0.7 minus 0.5 over 0.0913. Anybody dare to say what they got for that? 2.19 is what I got. So in terms of Z's, is that a little bit unusual? So if you were to draw your bell curve, how many standard deviations are you away from the mean? 2, a little bit, and then some, right? You're a little bit more than 2 standard deviations away. Does that make sense? So this is in the top what percent? Top 2.5. Remember that was 95%? Does that make sense?
Yeah.
So that's a little bit unusual, isn't it? Okay. All right. What if you're saying, how about you do the next one, because this one's not all that different. Anybody else get 0.0559 for standard error? Yes? No? Okay, and then for Z, .1 What'd you guys get for Z? That's what I got. How can you tell right away if your Z is going to be positive or negative?
The p hat smaller than p naught.
Yeah, if p hat smaller than p naught, then you're going to have a negative Z, right? If p hat is bigger than p naught, you'll have a positive Z. And is this guy unusual? Yeah, that's in the bottom 2.5%. Of the two, which is more unusual? The bottom one, because it's even farther away from the mean. Does that idea make sense? Okay, cool. So, suppose a two-sided test for a proportion resulted in a p-value of 0.03. What would the p-value be if the test was one-sided instead?
0.015.
P would have been half of 0.03 or 0.015, exactly. Of the two tests that we had above, part A, that would have been one or two-sided? Two-sided. And part B, in example 12.3, would have been one-sided. Okay, good. All right. So a Gallup poll released on October 13th of 2000 found that 47% of the 1,052 U.S. adults surveyed classified themselves as very happy when given the choices of, I don't know why I wrote very happen. Very happy, fairly happy, and not too happy. Suppose that a journalist who is a pessimist took advantage of this poll to write that the poll finds that U.S. adults who are very happy are in the minority, because minority means less than 50%, right? So if P is the proportion of all adults who are not happy, who were very happy in 2000, go through the 5 steps of testing to determine if this headline is justified. Okay. So are the conditions necessary to use a Z statistic for this test met? So the thing that you have to check, first thing is that you have a random representative sample. Yes or no? We're just going to assume yes, it's a pretty big size. And the second thing is that NP naught and N times 1 minus P naught have to be at least 10. And if we're talking about minority-majority thing here, what's the, at what percent do you go into being a majority? Like what's the breaking even point? 0.5, 50%, okay? So the null value, P naught, is 0.5. So 1,052 times 0.5, 1,052, 1 minus 0.5, are those both bigger than 10? Heck yes. Okay. All right. Part B says to find the test statistic. And so I didn't write on null hypotheses. I'm going to start with that. So H naught, HA. So H naught is that the proportion of adults who are happy is 0.5. And HA is that this number is less than 0.5. Because they want to say that they're in the minority, less than half. This is a confusing word, okay? This is a great question because it came up, I read some kind of sassy thing after the election somebody posted. So technically speaking, a majority means more than 50%. It doesn't mean the most votes or the most something. Even though I think if you broke this down into the 3 groups, 47% probably is the biggest group. It still isn't a majority because it isn't over half.
Right. My thing is P equals 0.5. If they were in the minority, wouldn't be in less than 0.5.
It's also okay to say less than or equal to 0.5. That's fine.
Okay.
The kicker is that the equal to has to go there.
Oh, okay.
That's all. Yep. But you get the whole, in terms of voting systems, when you win but don't have more than 50%, you're called the plurality winner. And whenever you put more than 3 groups out, it's really hard to be more than 50%. It's just a state. You can look back at all the past presidential elections, for example, and see that lots of people won and didn't get over 50%. Some countries deal with that by having a system called runoff ballots and stuff, but that's a totally different thing to talk about.
Would the null hypothesis not be greater than equal to?
Oh, yes, 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 sorry. Yep. I just was dyslexic. Yep, P bigger than or equal to 0.5. They're in the majority. Yep. Okay. So that's kind of step 1 is null and alternative. Step 2 is to find your test statistic. So is this going to be a Z or a T?
Z.
Z, okay. So P hat minus P naught over standard error of P naught. So what is P hat? 0.47. What is P naught?
0.5.
Over, okay, well, standard error of P naught, that's root 0.5, 1 minus 0.5 over 1052, which I got comes out to be 0.0154. I got negative 0.4545. Anybody else get that? No?
Negative 1.95.
Yeah.
Oh, okay, well, I'm wrong then. You else got negative 1.95?
I got that.
Okay, I's wrong. Happens. Don't push buttons right. Negative 1.95. Okay. So step 3 is to get your p-value. So that, oh, it's actually part C. Oh, okay, well, I'm just going to do it right here. So the p-value is the probability that your z is less than or equal to this negative 1.95. How likely is it you're going to get a number like that or smaller? And for that, you look at the z-table, right? Can you go on the negative side for 0.195? 0.02. Like this? Yes, okay. Steps 4 and 5 are to make a conclusion.
Which is part D.
Which is part D, yep. I just don't want to go to a new slide. And when on your test with making conclusions, you make the conclusion like, do you reject H naught or fail to reject H naught? And then what does that mean in the context of the situation? Both of those things. So do you reject H naught in this case?
Yes.
Yes. If alpha is 0.5, yes, you reject H naught. So that does mean that it is true. Oh, dang those newspapers. That the proportion of adults who are very happy is a minority, as in less than 50%.
But it's skewed because it's fairly happy.
Yeah, it's skewed because of the fact that they put things in 2 or 3 categories. I think that is still misleading, but it's not technically statistically wrong. Does that make sense? So we still have 20 minutes, and we can go early, but let me do one thing before you go. How about I make a list of all the stuff you have to know, and you just like write it down, make sure you get the stuff on your note card. Would that be helpful? Okay. Because I think I have a pretty good idea in my head of what's going on. And I can tell you the basic structure of the test.
Will this list fit on this piece of paper?
Probably.
It doesn't look like what you can borrow.
If I start writing, I'm not going to start.
Okay, so there's really just two basic ideas in this test. I know it seems like a lot, but it actually is you have confidence intervals and you have hypothesis tests, right? Okay. So the first thing we have is confidence intervals for what? Proportions. And of those proportions, you had two cases. One was just single proportion, right? The other one was the
P hat 1 minus P hat 2. Oh, okay.
right? That was the difference in proportions. Okay. Your multipliers here are they Z star or T star? Z star. And there was just a table that gave you kind of common ones like 98, 95, stuff like that. And here's the basic structure of the CI. You had P hat plus or minus Z star standard error of P hat, or P1 hat minus P2 hat plus or minus Z star standard error. Does that make sense? And how do you find the standard error of P hat?
Is it square root of P1?
It's just P hat, use P hat.
P hat, 1 minus P hat
Mm-hmm.
over.
Does that ring a bell? How do you find the standard error of P1 hat minus P2 hat?
P1 hat
P1 hat
times 1 minus P1 hat
over.
over N1
Yep.
plus P2 hat times 1 minus P2 hat over N2.
Yep. So one thing you'll have to recognize is this thing that I'm looking at, is it one proportion or two? Does that make sense? So that, in a nutshell, is confidence intervals for proportions. How about means? There we had three cases. What's the most basic case? Single.
Mu G.
Yep, single X bar. And then there's also
X
D bar, which is basically like X bar. And then the final one is
X1 minus
minus X2.
exactly. Okay, multipliers here are T star, and the basic structure is, well, X bar plus or minus T star, standard error, X bar. Same thing with D bar, right? Or X1 bar minus X2 bar. How do you find standard error X bar?
S over square root S.
How about standard error of D bar?
SD divided by square root.
And then how about this one? We just did this, yep.
And X bar 1 or plus S2 squared over N2.
Okay, or it's possible that you could have SP squared over N1, SP squared over N2. This is where the whole pooled thing comes in.
Are we going to have pooled on this?
I might ask a question about it. There was a question on the quiz about it, so it's free game. Does that make sense? But you get a note sheet, so just write the formula down for how you find it, and maybe you'll have to do it, maybe you won't. You use this when standard deviations are approximately equal to each other, when they're about the same spread. So that, in a nutshell, is the confidence interval thing. Is that okay? And you should know what happens to confidence intervals when you increase the confidence level or decrease the confidence level, stuff like that. Can I make a new slide now? Okay. Good? Okay. Other really big idea. Hypothesis tests. So in chapter 12, we had hypothesis tests for proportions. So the most basic case was one proportion. So something like H naught P equals P naught and HA P not equal to P naught, or P bigger than P naught, or P less than P naught. So you got to know about one-sided and two-sided tests. That part's not so hard. For these, what kind of statistic are you looking at? What is your test statistic? Is Z equals P hat minus P naught over standard error of P naught. Go back for just a second. One thing that was a little bit tricky in this, so I think one proportion wasn't so bad, right? Two proportions was a teensy bit tricky. So with two proportions, your H naught was that P1 equals P2, or how did we usually phrase that?
P1 minus P2 equals 0.
And HA was that either of those things are not equal, or there's a greater than, or there's a less than, one of the two, okay, but something. And the funny thing here is you have to estimate what your book called P hat, which is the value at which those two things are equal. Does that idea make sense? If you say proportion 1 equals proportion 2, you've got to say if one was 0.4 and one was 0.5, what is the average actual estimate? So the way you do that is you use the formula N1 P1 hat plus N2 P2 hat over N1 plus N2. And this is your null value.
Wasn't the null value always 0?
Kind of. So yes, but no, not really. There's not really a but. It's just that you need that to do the standard error. That's the thing. If you go back and look at chapter 12, this is specifically lesson 12-3. Like that's where I'm looking at this thing from. Because for your Z statistic, you have your P1 minus P2, like those things hatted, right? Your null value is definitely 0, like because you do You assume that these two proportions are equal, so this difference is 0, right? But then the thing that you have to divide by is the standard error of your null value, which is this p hat guy. So p hat minus p hat.
P1 hat minus?
Nope, it's this thing. Because kind of, suppose you had two samples you're testing, like, are girls more likely than boys to be left-handed, for example? And what this numerator counts is the number of lefties in your sample divided by your total sample of boys and girls. So there averages out the number of lefties in both groups. And remember how in the previous one this was standard error of P naught, right? So you've got to figure out what is this P naught thing. And the reason that that's 0 is you assume it's kind of like this estimated proportion minus estimated proportion. It's just that it cancels out to 0 because you assume they're the same. And so the place that this formula comes up, and by far the trickiest thing, is to find the standard error of the null value. You have to do this root p hat 1 minus p hat over n1 plus p hat 1 minus p hat over n2. That's the hardest thing. And I didn't have an example of that on the notes we did today, but if you look in section 12.3, example number 8, that's where we did one of those.
So is that n1 p1 hat, that's the denominator of the z value? The statistic?
Say that one more time.
Is the denominator of the z for that supposed to be SE p1 hat minus p hat?
No, it's SE of p hat minus p hat, because that's the null value.
Which is what you just did there.
Which is what I did right there, yeah. But it's kind of like how this one I have not SE of p hat, I have SE of p naught. Same idea, it's just that this p naught is p hat minus p hat. Yep, does that make sense? I know that's tricky. And that's the trickiest thing with proportions.
Would we have to put the 0 there if we know that they cancel out?
No, you don't have to write the 0 if you know they cancel out. That's totally fine. Like, I'll just check that you get the right answer and if you have the right work, if your answer is wrong.
So it's not always going to be a 0?
It will always be 0 for this kind of hypothesis because you're always assuming that the proportions are equal. That p hat is used in this piece right there. That's really where it's used. And your answer will be a little bit off if you don't do this because you'll have a little bit wrong denominator. That's what's going to be messed up.
So the null on top will always be 0.
Yeah, the null on top will be 0. Yeah, and that's because this null on top really is p hat minus p hat. Yep. Okay, and then the last one, and I think actually, I really do think that in this case, hypothesis testing is easier with means, really. I find that's the case. So for chapter 13, we'll say HT with means. What's your statistic now? Is it a T or is it a Z? T. And so we could have X bar minus mu over standard error of X bar. It's a little bit different then. So that's X bar minus mu over S over root N, right? Or what if you had differences?
G-bar.
Oh, I'm sorry. What if you had two population means?
X1 bar minus X2 bar minus.
Minus, which probably would be in this case 0, because you're assuming that there's no difference.
Over
Standard error of
X1 bar minus X2 bar.
Yep, and that could be pooled or unpooled, but it's the same as the confidence interval standard error. Okay. But the thing that I think, if you just be really careful about, is this guy. So that's the only thing that I think is seriously tricky. And then, because I want to tell you one last thing before you go, also make sure you know what a type 1 error is and what a type 2 error. Those things should both be in your notes. I explain what it means to make both of those errors. Okay, sorry I ate up all your time.